Hello everyone, my name is Huiqing Wang. I'm from the Building Acoustic group of Eindhoven University of Technology. Today, I would like to present my work on wave-based room acoustic simulations of an open-plan office. Here is the outline of my talk. Firstly, I will introduce the background and the purpose of the study. Then a brief introduction of the used wave-based room acoustic modeling method is presented. After that, the comparison between the simulation and the measurement results are shown. Finally, some concluding remarks. Recently, the wave-based time domain discontinuous Galerkin method has been applied to room acoustic modeling, and the necessary formulations of acoustic boundary conditions have been developed. However, previous experimental validations has only been performed within an empty reverberation chamber. A comprehensive evaluation of the scheme involving complicated boundary materials is still missing. Therefore, in this study, the time domain DG method is applied to simulate the acoustics of a large real open plan office in the low frequency range. It aims to assess the accuracy and applicability of this wave-based method for realistic sound field analysis. The ground truth references to be compared against are measurement results, which have been previously published in a study on how room acoustic parameters are affected with varying configurations of furniture and sound-absorbing barriers. As you can see from the bottom figure, the simulated open-plan office has a long and narrow floor plan. The room has a sound-absorbing ceiling with 20 mm rock-formed panels with a 500 mm cavity. The floor is covered by carpet. It has 5 workstation islands with gypsum dividers and side panels, which are installed for the sake of privacy. To increase sound absorption, 30 mm thick melamine foam is applied to both sides of the upper part of the dividing panels that are along the y direction. Small closed rooms indicated by the blue areas subdivide the long space. The source and the receiver locations are denoted by the red and yellow circles respectively. In this study, 2 variations of the furniture setups are considered. In the first configurations, only tables are present in the room. In the second configuration, all the furnitures, as mentioned above, are installed. An omnidirectional sound source for model B&K4292 and microphones were used for the measurements, which have been performed following the ISO standard 3382. More details of the geometry of the office can be found in the reference. In this slide, I will briefly introduce the main ingredients of the wave-based time domain discontinuous Galerkin scheme, which are used to numerically solve the governing linear acoustic equations. As a first step, the equations are rewritten in a conservation form. Then, the unknown solutions inside each of the elements that tessellate the computational domain are approximated with local polynomial approximations. The weak formulation is obtained by the orthogonal projection. In our work, the upwind numerical flux is used. The semi-discrete system is finally time integrated using the Taylor series time integration, where all the needed time derivatives of various orders are obtained based on the arbitrary high-order derivatives methodology. More additional details can be found in the reference. Accurate modeling of boundary conditions is of critical importance for acoustic simulations. In this work, the acoustic properties of the absorptive surface materials, including ceiling, foam, and the carpet are measured in a reverberation chamber according to ISO 354. Their values in octave bands are shown in the table. For other sound-reflecting materials, such as windows, doors, gypsum boards, real value impedance are used. It should be noted that the measured Sabin absorption coefficients are energy parameters that do not carry phase information. However, for wave-based simulations, the complex valued surface impedance or complex reflection coefficients are needed for the boundary modeling. Furthermore, there are infinite number of surface impedances that yield the same absorption coefficient. To address this issue, we assume that the measured Sabin absorption coefficients correspond to the size-corrected absorption coefficients for the intrinsic low-frequency range. Furthermore, we assume that all the boundary materials are locally reacting, meaning that the surface impedance is independent of the angle of incidence. Here is the simulation setup. Due to the considered low frequency range, only objects that have a dimension larger than half a meter are considered. It indicates that all the thickness of the tables, gypsum boards, and foams are neglected, which will be modeled as fictitious 2D floating surface in the geometry model. Unstructured tetrahedral conformal mesh are used. For the spatial discretization, a 6-order polynomial basis is used, resulting a point prevalence of around 11 for the 500 Hz. For the time integration, 5th-order Taylor series integrator is used. To accelerate the simulations, all elements are divided into 2 groups based on their size. The local time-stepping scheme is used to integrate the fine and coarse elements in time with their corresponding time-step sizes. In the simulation, the dodecahedral source is modeled by an initial pressure pulse of Gaussian shape. To correct the spectral characteristics of the impulse source, simulated responses are deconvolved to get the impulse response. Here are the comparison of the results from the measurements and the simulations. They are firstly evaluated in terms of standard room acoustic parameters, including reverberation time, early decay time, clarity, and the center of gravity. Spatial average of the considered room acoustic parameters and their standard deviation of both configuration setups are shown in the table. The values before the slash are the measured ones, while the after slash are the simulated ones. The first impression of the comparison results is that none of the simulation results match the measured ones very well, except for the center time at 125 Hz, which indicates the balance between clarity and reverberation. Large deviations are observed for spatial mean values of both reverberation time and early decay time, which are directly calculated from the energy decay curve. For T30, lower values are predicted compared to the measurements for both setups in the 125 Hz, whereas higher values are found in the simulations for the 250 Hz and the 500 Hz octave bands. For the open plan office, good speech privacy between workstations is of primary concern. Therefore, the spatial decay rate of speech and the A-weighted sound pressure level of speech at a distance of 4 meters away from the sound source are investigated, as described in the ISO standard 33823. The sound power level of the loudspeaker and the simulation impulse source are normalized based on the sound pressure level at a distance of 1 meter in the free field condition. Due to the limited frequency range of the wave-based simulations, the logarithm summation of the A-weighted sound pressure level is calculated only up to 500 octave band, instead of 8,000 Hz for both simulations and measurements. It can be seen that the simulations have a lower predicted sound pressure level of normal speech for all receiver locations except the 8th receiver. The discrepancies get smaller at further distance. Furthermore, the simulated spatial decay rates of speech are smaller than the measured ones in both cases. For the first configuration setup, the monotonic decrease of the awaited sound pressure level is well predicted, while a fairly good agreement of the zigzag shape in terms of the sound pressure level is observed for the second configuration. It indicates that the effects of the table dividers and side panels are taken into account in the simulations. As we have seen, the simulation and measurement results do not match quite well. Well, it is difficult to pin down the exact reasons for the deviations. Here we list a few factors that explain the discrepancies. First of all, there are inevitable uncertainties and inherent randomness in the measurements. Another reason is that the simulation inputs are not sufficient. In this study, the exact size of windows are not measured. Also, the measured absorption coefficients are only available in octave bands, and a monotonic frequency dependency is assumed for the narrowband. Furthermore, the accurate phase information of the surface impedance is missing. Lastly, the current wave-based simulation model all surfaces as locally reacting. However, for the considered office, grazing incidence might be more pronounced in the early reflections. The suspended ceiling has a large air cavity behind it, which may exhibit strong extended reaction. To summarize, wave-based room acoustic simulations of a real open-plan office in the low frequency range has been performed with the time-domain discontinuous Galerkin method. The acoustic properties of materials are represented with energy-based absorption coefficients in octave bands, which are measured with the reverberation chamber method. From this input data, the required complex valued surface impedance data is retrieved by fitting the size-corrected Sabin absorption coefficients, assuming a monotonic absorption behavior within the interested frequency range. Noticeable discrepancies between the simulation and measurement results are observed, especially for the reverberation time and early decay time. As for future work, experimental validations with increasing level of complexity of room scenarios will be performed. Furthermore, the formulation of extendedly reacting boundary conditions should help to achieve more satisfactory improvements in the simulation accuracy. Thank you for your attention.